is here now.
Hello, Mrs. Stewart, how are you?
I'm doing good. How are you?
Are
Sorry,
you
I'm
ready
late.
for us, huh? That's good. Welcome.
Thank you so much for having me.
Okay, so Dr. Chen, it's up to you now.
Okay, yeah.
Let me just ask one question. Beatrice, were you going to record this
It's
and post it?
recording.
Oh, it is recording.
It's recording right now.
Okay.
Did you see on the top of the screen recording?
Oh, I see it. I was looking at the right side. I need to look at the left side.
Okay.
All right, very good. Thank you.
Okay.
Okay, good. Thanks for inviting us to this webinar. We are very excited and honored to talk our research in this webinar. And before we get started, I think we want to do an introduction for ourselves. First, my name is Hui Chen, and I'm currently a postdoc in Dr. Lee Blaney's group. I've been doing research in Blaney lab for 1.5 years now, and my research is about nutrient recovery from wastewater by donor dialysis, and I'm mainly focused on doing advancement for donor dialysis reactors for improved nutrient recovery. And for donor dialysis reactors, I will talk about, I'm talking more in my future slides. And yeah, that's about me. Usaf, do you want to introduce yourself a little bit?
Sure, yeah. Hi, everyone. Good afternoon to all. I'm Utsaf Shashwat. I was a PhD student in Dr. Blaney's lab, and I'm currently a postdoc at UC Berkeley. Yeah, so I'm on the West Coast right now. And I'm going to talk about some of my research that I performed during my PhD. So I won't get into the details right now. But yeah, I'm excited to be here and look forward to engaging with you all.
I think next can be Michael Fleming.
Yes, hi everybody. My name is Michael Fleming and I'm a PhD candidate in Dr. Lee Blaney's lab, also on the nutrient recovery team. And my research topic is sustainable recovery of ammonium from agricultural and municipal wastewater by donor dialysis. I can pass to, who's that, Oriel?
Hi everyone, my name is Oyen Dalampa. I am a senior at the University of Maryland, Baltimore County, and I work in Dr. Blaney's lab in the nutrient recovery team as well. I will pass it to Kaden.
Hi, good morning, everyone. Sorry for my voice. I'm feeling like a bit under the weather lately, but my name is Kaylin. I'm a junior chemistry major at the University of Maryland, Baltimore County. I've been in the Blaney lab for about a year now, since last fall, and I currently work with Hui on the nutrient recovery process, and I'll mostly be talking about later scaling up the donor dialysis reactor configurations.
Great, thank you all for introducing yourself. And yeah, we are going to start our presentation, and our presentation is going to be a 5-in-1 presentation. Like audience, you guys can just type your questions into the box, Q&A box, and then we're going to answer it at the end. So let's get started. Can you guys see my screen now?
Yes.
Yes.
Okay. All right. So our topic today is circular nutrient economy. Yeah, let's get started. Before that, let me my laser point. So our research group is mainly focused on 2 areas of environmental chemistry and engineering. The first area is contaminants of emerging concerns, and the second area is the recovery of vital sources such as nitrogen and phosphorus from different waste streams. So today we are going to focus on the second area. So the reason why we are doing nutrient recovery is because nutrient pollution is becoming a worldwide problem. And it really impaired environmental quality. So we really want to develop some recovery processes to offset these pollutant loads and also produce valuable products to achieve the circular nutrient economy. And in my work, I targeted the urine as my wastewater because it contributes a majority of nitrogen and phosphorus in raw wastewater. Then to achieve a more sustainable handling of nutrients from urban wastewater. So you can take a look at this chart. This is the synthetic urine recipe we used in the research, in our research. So ammonium, potassium, phosphate, they are all there. So we expect to recover these nutrients from the urine and then to precipitate some solids, like kind of like fertilizer for the future use. So the technology we are using is donut dialysis. And let's talk about donut dialysis. And this is a figure, like a scheme showing how the donut dialysis work. Usually it has two chambers. One is called waste, one is called jaw, and we also call it recovery. And these two chambers are separated by an ion exchange membrane. And in this case, this membrane is modified with positive charged functional groups. So the anions or like negative charged ions in the waste side can transport through this anion exchange membrane to this side. And also the anions in the recovery side can also transport to the jaw, to the waste. So because of the chemistry of this membrane, like cations or any solids, they will be totally blocked by this membrane. So donut dialysis can really achieve a selective removal of either cation or anion. And the driving force for donut dialysis is based on the electrochemical potential gradients of this of the target ions in the waste chamber and the jaw ions in the jaw chamber between these two solutions and cause them to transport across this membrane, enabling the nutrient recovery into a cleaner jaw solution. So for example, you can see this is divalent phosphate, and this is like in the waste side and in a dirty waste solution. And in the recovery side, we usually use sodium chloride as our jaw solution. So chloride ions as a jaw ion can be exchanged to the waste for the divalent phosphate to come into the jaw. So in general, a higher jaw ion concentration, for example, here, the sodium chloride content in the recovery chamber, it can really increase the extent of the nutrient removal or recovery. The reason why we use this technology is because the biggest advantage of donut dialysis, it can achieve selective removal of target ions, as I mentioned, without high chemical and energy costs, because this whole process is non-pressure driven. And since it's the mechanism, like it's based on electrochemical potential gradients, so and also it won't cause any secondary pollution. Yeah, so with that knowledge, recently in our lab, we developed this tubular membrane reactor. It's a little bit different what I just mentioned in the previous slide. So this reactor is like a little bit advanced than the conventional donut dialysis reactor because we want to achieve simultaneous recovery of cations and anions at the same time from the waste solution. Here is the urine. So let's take a look at the scheme. We have a waste tank containing 30 liters of the synthetic urine, and the membranes, or we call it tubular membrane, and these tubular membrane, they are hollow. So we can pass the jaw solution inside, and this whole tubular membrane is immersed into this waste tank. And we also have a jaw tank containing 5 liters of sodium chloride solution. These two chambers are totally separated, and the jaw solution is continuous pumping into this hollow tubular membranes. So with this design, both cations and anions in the waste tank, they can kind of recover like through this anion membrane and cation exchange membrane to the cleaner jaw solution, jaw tank. And then at every 24 hours, we will dose some magnesium and also adjust the pH to 9. So because we want to see if we can precipitate the solids at the bottom of this jaw solution. And yeah, this is our scheme. And this here is the real setup of this reactor in our lab. Everything is matching with this scheme. But here we have a pump because we have to pump the solution, like the jaw solution, into this tubular membranes. And let's take a look at the data. So here is showing the phosphate concentration in either waste tank or jaw tank along this operation time. So we operated 100 hours in total, and the y-axis is showing the concentration of the phosphate. And the yellow circle here is showing the phosphate concentration in the waste side, and the blue triangle is showing the phosphate concentration in the jaw. So in the waste, the phosphate concentration is keep decreasing, which is very promising because it indicates that phosphate is removing to the jaw. And then in the jaw side, you can see it's like initially it's increasing in the first 24 hours, and then it will experience a sharp decrease at 24 hours. That's because we dose some magnesium and we adjust the pH to 9. So the aqueous phosphate concentration is decreasing because it forms some solids. This is very exciting, and it's also we also observe this like precipitation event at every 24 hours. So 24 hours, 48 hours, 72 hours, and 96 hours. Here, from this figure, you can see like the concentration of phosphate in the jaw is higher than the concentration in the waste. That's because we used a different volume of the waste side and jaw side. So the jaw volume is 5 liters. It's much smaller than the waste solution. And the reason why we use this like a smaller volume, the jaw tank, is because we want to create a concentrated jaw solution, and then it will facilitate the nutrient precipitation. It is also interesting to see that right after the precipitation event, there is a rapid recovery immediately. You can see here, this is like a rapid recovery right after the precipitation. That's because the concentration gradient reestablished so it will enable this continuous recovery. Other than phosphate, other nutrients such as ammonium, potassium, magnesium, and calcium, they will also recover into the jaw solution and facilitate the recovery of solid fertilizers. So very similarly to the phosphorus, you can see for all of these cationic nutrients in the waste tank, their concentration is keep decreasing. However, in the jaw side, it will increase first, and then at every 24 hours, there is a decrease. It's showing something happen, like this nutrients are precipitated out into the solids. But for magnesium case, you can see at every 24 hours here, like there is an increase. That's because we dose magnesium in. So these results are very exciting, which indicated that okay, the nutrient in the jaw side has been precipitated out, and so we are wondering, okay, what's the solids here? So based on the chemistry, we thought, okay, probably struvite and potassium struvite is precipitating based on these equations, but we need more characterization skill to figure out the like composition of this solid. So we get the solids and we freeze-dried it and submit for SEM and EDS analysis. So SEM figure here showing us most of the solids are in needle-like and some of them are in flake-like. Then we did EDS, which can tell us the elemental composition of these solids. So based on the elemental composition ratio, we can see that most of the solids are in struvite form. And based on the precipitate amount of those elements, we got 75% recovery of struvite. Besides that, we also did some modeling by visual mean tech to confirm the precipitation. So as you can see, around pH equal to 9 here, struvite is the main precipitate. And then we compared our experimental result with the predicted result. Here is the figure. You can see most of the nutrients aligned. I mean, the experimental result is aligned with the modeling result. And from experimental result, we also got more potassium recovered and less calcium recovered, which is also very promising for future. Oh, I forgot to mention that struvite is like a phosphate mineral, and it's a very common fertilizer. So this study really gives us the promise that we can achieve nutrients from the urine system by donor dialysis. Okay, that's all for my part. Now, if you have any question for me, you can save your question to the end, or you can just type your question into the Q&A box. Now I'm gonna hand it over to Kelly.
Let me interrupt you a little bit, and we have one attendant that has a question.
Okay.
If you open questions and answers, you should be seeing the question in there.
Yes.
I noticed from your table early in your presentation that urea is the major component of urine, 25%.
Mm-hmm. Is urea part of waste after dialysis? Is recovered for recycling? Okay, so in our recipe, our recipe is for fresh urea, which means there are the major composition of this synthetic urine is urea, and the urea is not, and the urea is a compound. It doesn't contain any charges, so we assume that there is no urea will be extracted to the draw side. Yeah, so it's gonna stay in the waste part.
Okay, thank you. Is there anyone else that wants to add to that answer, or shall we continue with the next presenter?
Oh, I saw one more question. Without precipitation step, does diffusion decrease as an equivalent is reached? Without precipitation step, does diffusion decrease? Do you mean the transfer of the ions will decrease as an equilibrium is reached?
I feel, are they talking about the equilibrium gradient being reestablished as the precipitation happens in the draw solution? You know, your draw concentration goes down, so it reestablishes the electrochemical gradient. So how does that affect the diffusion compared to if there's no precipitation? Then does the rate decreases slowly? I believe that's the question.
Actually, I don't think the precipitation step will affect the diffusion process. Yeah, I think the diffusion should keep same. Sorry for what I'm remembering, likely impacts inside.
Could you repeat that, please? I couldn't hear very well.
Okay, I saw another comment.
Yeah. And one thing I see in your plots, Hue, which I think I also observed, like when you do the precipitation, it seems like after there's a drop in the concentration, you still see those lines are very parallel, which to me seems that the rate of recovery is kind of consistent even after you're doing intermittent precipitation. But I guess, yeah, we'll have to measure the concentrations as well.
Yeah, that's right. Okay. All right. Is there any more questions?
Apparently not. You may continue.
Okay. So let me stop sharing first, and then yeah. Now it's Kayleen's turn.
All right, thank you, Hui. Again, apologies for my voice. I just woke up this morning and I was like, oh my gosh, not today of all days. I was feeling like I felt something coming on yesterday, and then today I was like, oh, here we go. So hopefully, it's not like I don't get too sick or anything, but just bear with me, please. Okay, what I will talk about today kind of builds off of what Hui mentioned with recovering nutrients from synthetic urine, but I'll be talking about the need to scale up that process of donor dialysis, especially when it comes to Maryland in particular. I think this is like a perfect opportunity to bring the motivations behind this research and relate it to Maryland. In September, or from 2018 to 2019, there were around 500 million pounds of nitrogen delivered into the Chesapeake Bay. At these levels, we can consider them to be nitrogen pollution. And most of the nitrogen pollution came from agricultural runoff. Around 42% of nitrogen, as well as 55% of phosphorus entering the bay comes from agricultural runoff. And this is a major problem because it's polluting our bays and with excess nutrients. Maryland legislation actually processed essentially a cleanup blueprint, and lately we haven't been necessarily achieving those goals of that blueprint. For example, in 2021 alone, only 1.1 million pounds of nitrogen was produced. So it would take 40 years to actually reach the goal that we wanted to. If we wanted to reach that goal by 2025. So there's an essential need to scale up the process of trying to remove these excess nutrients from these water systems. And our lab essentially does that. And we designed and created what we call tube-in-tube membrane reactors. Sorry, the faces are in the way. I'm trying to move them so I can see. But okay. So in the scheme on the left, we have our waste solution, which in our case, we looked at synthetic urine, which is similar to what Hui was describing. And we have our two draw solutions here. One is going to contain anions that we removed from the waste solution, and the other is going to contain cations that we removed from the waste solution. In the middle, we have these tubular reactors where we have an outer tube and an inner tube. The outer tube is where we flow our waste solution through, and the inner tube is essentially wrapped with either a cation exchange membrane or an anion exchange membrane, and that is where we run our draw solution through. So essentially, we can still achieve the simultaneous recovery of the cations and the anions from our waste solution. But if you look in the table on the bottom right, we can see that the surface area to volume ratio, which can contribute to, or which can affect the removal and recovery of our nutrients, the efficiency is the tube-in-tube process has a higher surface area to volume ratio. So we expected to achieve or to improve these recovery efficiencies using our tube-in-tube reactors. In the upper left or upper right, that's just showing a real life scheme or a real life figure of what it looked like in the lab. And so we have our two reactors. In this case, it's just one reactor of the cation exchange membrane and the other with the anion exchange membrane. And we have our pump that pumps our draw solution and our waste solution through these membranes or through these reactors. To dive into the data, and so like I said before, the waste solution that we used was still synthetic urine to build off of Quay's research. These figures just show ammonium, potassium, calcium, magnesium, and phosphate removal. And the figure F just shows the struvite that we had collected during these processes. And so as you can see in the figure, the blue triangles represent removal of the ions from the waste solution, and the other orange circles represent recovery of those ions into the draw solution. So with only using one reactor or one cation exchange membrane and one anion exchange membrane tubular reactor in this schematic, we were only able to achieve around 60% of ammonia and 45% of phosphate recovery after 11 hours, which is lower than what we had expected, especially to the tubular membrane reactors like Quay was talking about. And so we wondered, oh, could we improve these recoveries by scaling up our process? Because our schematic is essentially modular. If we add more reactors, we are able to treat a larger volume of our waste solution and achieve higher recovery efficiencies. Or at least that's what we had expected to see. And that is actually what we did expect, or what we did see after we tried to put two reactors in sequence with one another. So it's the same synthetic urine solution, but we were able to achieve recovery after 8 hours, which was an improvement from just using one reactor pair in sequence. And we were also able to improve our recovery efficiencies. We were able to achieve around 75% or 70 to 75% of removal of ammonium, potassium, and phosphate. We are continuing to scale up these reactors by just putting more of the reactors in sequence with one another and seeing how much we can improve those recovery efficiencies. And I guess I'll pause for questions. That concludes my part. Are there any questions in the chat?
Okay. There is one question that it was left unanswered from the previous presentation. Maybe we could answer that one before we continue with the questions for Mrs. Stewart.
Yes. Yeah. I can answer it now. So the membrane won't impact the establishment of an equilibrium. The equilibrium is depending on the concentration gradients, electrochemical concentration, like chemical gradients of these waste ions in the both sides. Yeah. So the membrane won't affect this establishment of an equilibrium. All right.
There are no questions so far for the second presentation, but I do have one. I would like to know how does the city or how is that the nitrogen pollution is determined? What do you see in the environment that you see, oh, we have nitrogen pollution? Or is it something that you just have to grab the water from streams or some samples from soil, or what? How do you get that?
Sorry, I am actually not completely sure on how these statistics are determined. I would think it would be from taking samples from the bay, but it seemed like it was on a larger scale than just like taking samples, because it looked like you're measuring like how many pounds of nitrogen are put into the bay over time. So I'm actually not sure how those statistics are determined, but that's a great question to look into further. I'd have to do further research on that. But if any of the other panelists, I don't know, but I don't know if anyone else knows.
So let me reframe. Beatrice, are you asking like what are like the visual signs in the environment to just say that? Are you talking about like eutrophication as a result
Yeah,
of
it is evident that there is a problem.
Right.
And how do they notice the problem?
Right. One of the things, I'll just add is eutrophication or formation of these harmful algal blooms that happens, at many places across United States. You say the Gulf of Mexico. We got that in the San Francisco Bay this summer. Then we have that in the Great Lakes as well. So nutrient pollution is pretty prevalent in and it's impacted by both agricultural runoff, where you have nutrients coming from application of fertilizer, but then also, in many countries, it's as a result of, other point sources as well. So that's one of the, concerns coming from nutrient pollution.
Yeah, if I were to add to that, you also have the phosphorus management tool, which is a Maryland regulation that provides like a scientific method of determining the phosphorus concentration in soil. And depending on those soils that measure high in phosphorus content, then those farmers are restricted from land applying manure, for example, to those soils to mitigate agricultural runoff. So you do have specific scientific methods of measuring phosphorus. I'm not sure about nitrogen though. I'm not sure if there's a similar test for nitrogen to quantify how much nitrogen is in agricultural runoff.
Okay, thank you. Dr. Shen?
So let's see, I think we got 2 more open questions here. So first one, how familiar in composition are synthetic urine in agricultural runoff? So the synthetic urine recipe we used is based on the fresh urine, and agricultural runoff is, I think it's different, but my target is synthetic urine. I think Usaf and while Usaf and Michael gonna present, and their target is different. So yeah, you can wait until their presentation, I guess.
Yeah.
Okay.
Wait, can I add one thing to your response? Yeah, because I currently in my role as a postdoc, I work with urine. So, I might just add a sentence like synthetic urine is typically, we don't collect synthetic urine, right? It runs off into a wastewater treatment plant, and there some nitrogen is removed, and then it's discharged into a water body. But the idea is synthetic urine is very concentrated source of nitrogen, and the attempt is to capture it at the source itself, because it's much easier than agriculture runoff, where you have a low concentration of these nutrients compared to urine, but you have no way to control. You might have some management strategies. So that's why people are very interested in synthetic urine, because it's a point source, very concentrated, a waste resource.
Yeah, good. What efforts are focused on treating the material to be recycled to improve the quantities of recovered materials? What efforts are focused on treating the material to be recycled?
Well, maybe we can go with the other 2 presentations that you mentioned, and then maybe we can get the answers from there, or otherwise we can go back at the end of the presentation. Okay?
Mm-hmm.
Okay, sure. All right, yeah. Let me share my screen. All right. So hello, everyone. I'm Utsav again. And as I said, I was a PhD student in Lee's lab. And, the donor analysis process in particular is pretty close to my heart, because, it was when I was in the lab, we started working with the process. So I'm really glad to be part of this webinar and to see my former colleagues, have moved into many different directions, and the results that they're presenting is really heartening, because some of these things I couldn't imagine when I was working as a PhD student, and there were many unanswered questions. So really excited to see all that. And for my presentation, I'm going to go back to my PhD research, and we are, what I did was more into how we can modify the waste chemistry itself to improve the recovery of a nutrient. So in this particular case, I was particularly interested in looking at sewage sludge, because it's generated in massive quantities, and it, compared to some of the other waste resources, sewage sludge has a relatively high concentration of phosphorus. But in spite of that, it is not a great land amendment, because the phosphorus that is present in the sewage sludge, it's bound to metals. And I'm going to talk a little bit more about in the subsequent slides. The other factor is sewage sludge has a lot of organic matter. As a result, it has very low nutrient density. And then you have presence of contaminants, such as CECs, which are contaminants of emerging concern. I'm sure even if you're not aware of CECs, you probably have heard of PFAS, which seems to be one of the favorite chemical among the environmental chemists and engineers these days. So you have all of that present in sewage sludge as well, which make it unsuitable for use in agriculture. So I was looking into employing Donan dialysis and seeing if I can selectively recover phosphorus. So for my study, I used alum-laden waste-activated sludge. And just to give a brief background here, alum is typically added in the wastewater treatment plant to reduce the phosphorus levels before the liquid is discharged into a water body. So what it does is binds a lot of the phosphorus in the solid phase. And I was looking into if we can recover these solids. So these green circles represent the phosphate and the pink is the waste solid. So the phosphate bound to the solids, can we recover these solids through Donan dialysis into a much cleaner draw solution, which in this case, I was using a sodium chloride based draw solution. And one aspect or one novel aspect of my work was to employ ligands. So, some of you or, many of you might be familiar with these organic molecules called ligands. So for example, citrate here is an organic molecule which have a very high affinity for metal ions. Now, part of my hypothesis was that if we introduce these ligands into the waste suspension, these will interact with the metal ions, in this case, aluminum. As a result, the sludge will partially dissolve and it will release the phosphate ions that was bound to the solid phase. And then this can be subsequently recovered into the draw solution. And here I was interested in answering two particular questions. One was how effective are these organic ligands in releasing the phosphorus from alum-laden waste-activated sludge? And then if I combine it with Donan dialysis, what is the recovery efficiency that can be achieved? So to perform these experiments, I first created synthetic sludge, and this was generated by adding aluminum and phosphate salts. The aluminum to phosphorus ratio was maintained around 5:1. This is typical ratio that we see even that operators employ at a wastewater treatment plant. So when you prepare these things, you can see there's a liquid phase and there's a solid phase, and the phosphorus is mostly bound into the solid phase, over 98%. And the solid is composed of two different kinds. One is aluminum hydroxide, and then you also have aluminum phosphate. So once we generate the synthetic sludge, we conduct these 4 different experiments by adding these 4 different organic ligands: acetate, citrate, EDTA, and oxalate. And I chose these ligands based on their different physicochemical properties, their size, and then most importantly, their affinity for the aluminum ions. So I dosed different concentration of these ligands from 5 to 100. And I hope you can see at the end of my experiment. So this snapshot is at the end of the 24 hours. You can see these suspensions look very different. You have a much clearer suspension at higher concentration. So in fact, I still vividly remember this. When I was conducting these experiments, I was so excited, like, oh, there's something happening. When you see these differences in the solution, there's something happening. And and that's the reason I love working with synthetic suspensions. Every time we perform these experiments, you get really nice results. But I promise I'll also present as a little bit on real sludge in my subsequent slide. But coming back to this, we saw these results. We saw that these suspensions have very different turbidity based on the ligands we are using. For example, acetate, we don't see any change in the turbidity of our suspensions. Whereas when we add citrate and EDTA, we see there's a sharp change happening around 20 or 30 millimolar. And we see that happening for oxalate at a much higher concentration. So the next question in my mind was, okay, so if you're seeing this visible cues, what is the concentration of phosphorus in our solution? So we measured the concentration of phosphorus and aluminum. And on these plots, you can see citrate on the x-axis, increasing concentration of these ligands, and then increasing concentration of aluminum and phosphate. So for citrate and EDTA and even oxalate, you see that at low doses of the ligand, you don't see any phosphorus coming out into the liquid phase. Then you see a sharp increase, and then the phosphorus concentration saturates where it reaches maximum. And this corresponds to your phase where you have a totally clear solution. And you see this for EDTA. For oxalate, you see this happening at a much higher concentration, which kind of correlates with the picture I showed you, where you see a change in turbidity happening at a much higher concentration for oxalate. And you also see that aluminum concentrations are increasing for all these ligands. One thing we did not observe, we did not observe any change for acetate, which indicated that acetate is not an effective ligand when it comes to binding with aluminum and dissolving the sludge to relieve phosphorus. So as I said, the final part of this study was to look what happens when we combine it with Donan dialysis, and then we do it for real alum-laden sludge. So I'm showing this 2-chamber reactor here where we introduce the ligands on the waste side. And I'm showing the picture of the waste suspension and the draw solution at the initial time, which is t is equal to 0 R. And at the end of my experiment that was t is equal to 300 Rs. So one thing I want to highlight, if you look at just visually, you see not much change happening here for waste activated sludge in terms of the color. Maybe it's gone a little bit lighter. For the draw solution as well, you start with a very clear, clean solution, and then at the end of the 300 hours, you see very little brown color in the draw solution. Now, this brown color originates from the presence of dissolved organic matter. So which means that in the Donan dialysis process, when we use these anion exchange membranes, we are getting very limited or very minimal dissolved organic matter permeating through the membrane. So that's promising, but we were interested more into seeing if we are able to selectively then recover the phosphate out of the waste solution. So the plot on the right-hand side is the mass distribution in the waste solids, waste solution, and how much mass of phosphorus was retained in the membrane and how much made it through into the draw solution. So I hope you can see when we added, when we just had waste activated sludge, which is a control here, we see most of the phosphorus is still part of the waste solid, even after 300 hours. Whereas when we introduce these ligands, we see 25 and 45% of the phosphorus coming into the draw solution. So this was really promising because now we are showing that we have limited amount of dissolved organic matter making through the membrane, but we have a much higher proportion of phosphorus, a percent of phosphorus coming into the draw solution, which indicates selective recovery. And once we have this draw solution, which now has a high concentration of phosphorus, we can feed it into a precipitation reactor to precipitate out phosphorus from this much cleaner matrix. One final thing that I want to mention, these ligands perform well, and we also conducted some preliminary economic analysis. I guess that's one of the questions with every technology, that you can propose something novel, but does it make economic sense? I'm not going to present the results, but the numbers suggested that this is much more cost effective than using acid or base dissolution methods, where you need a much higher concentration of acid to lower the pH or increase the pH through addition of base. And so in terms of cost, if we are employing some of these commercially available ligands, we can reduce the cost of this process of recovering phosphorus. All right, that was my part, and I'm happy to hand it over to OAL. But before that, if there are questions, I'll take those. Thank you.
Thank you, Usaf. I think there is a question for you from Camila Rojas.
Sure.
Nice work. Is the binding affinity of aluminum for these organic ligands known? And if so, do they correlate with your findings?
Right. Yeah, thank you for the question. I think that's a very, very relevant and important question here. Yes, the binding affinity is known. There are equilibrium constants available for a system where aluminum and the ligand is in the aqueous phase. Yeah, when we perform these, that's why if you see some of these results, I forgot to mention that, but these solid lines that you're seeing are the model. So we model this behavior in a chemical equilibrium software, and we see a very close alignment between the data and the model here, which indicates that it aligns with the equilibrium constants that are available, and also that this model can be now used for much more complex waste matrices. If we know the inorganic composition, we can predict how much ligands will be used if we need to release phosphorus from different kinds of waste matrices.
Great. Yeah, and let's see. Yeah, I guess that's the question for you. Now we can hand over to Oriel.
Sure, thank you.
Thank you. I'll share my screen. And I hope, yeah, you can see my screen, full screen.
Mm-hmm.
I think it's not in full screen. Yeah, now we get it.
Now it is in full screen.
Yeah.
Okay.
Thank you.
Thank you, Sal. So great presentation, Sal, and I like how you emphasize on like the selectivity, which is something I'm also going to talk about in my future slides. Utsav, Wei, and Katie talked about nutrient recovery, and they also touched on the issue with pollutions. And I'm just going to add one more motivation behind the recovery of nutrient. Here we are looking at the importance that nutrients such as nitrogen, phosphorus, and potassium have on food security. They can be recovered in form of fertilizers such as struvite particle that I believe Wei and Kaylin mentioned. And 1 second, I'm going to change my pointer. So when they are recovered, we can have we can recover them in the form of fertilizers, which are needed for food security. With the growing population, we have increasing need on supplying enough food to feed the world population. And another aspect that is related to nitrogen specifically is that the National Academy of Engineering has identified closing the nitrogen cycle as one of the grand challenges that engineers need to tackle. Consequently, the work that we do in our lab is contributing to solving bigger issues that affect the entire world. And it has been rewarding for me to participate in this project. I specifically work on ammonium recovery from waste and wastewater. And one way we want to recover ammonium as well as the other nutrients such as phosphorus is in the form of struvite particles or potassium struvite. Previous studies have shown that applying previous studies have compared the application of struvite particles as fertilizers compared to conventional fertilizers to crops. And what they showed was that when struvite was applied to crops, the nutrient runoff was less than when conventional fertilizers were applied to crops. Another thing they noted was that the nutrient uptake by plants favorized better plant growth when struvite was the fertilizer compared to when conventional fertilizers were applied to crops. In my work, I use the Donen dialysis reactor to recover ammonium. Wayman mentioned this setup before, but I'm going to go over it for my specific system. In the left figure here, you can see that we have the green that represent the chlorine ion. The yellow color is for ammonium and the purple is for sodium. And the feed solution is wastewater in our case, and it has ammonium ion in it. And in the DOR solution, we are trying to recover the ammonium by replacing some of the sodium ion, and they cause a membrane that is selective to only positively charged ions. So like as you can see here, chloride is not able to cross the membrane, and at equilibrium, we reach a point where we have recovered a significant amount of ammonium and replace some of the sodium in the DOR solution by ammonium ions. I looked at two membranes that have different properties. So the CMI 7000 membrane and the Nafion 117 membrane. The CMI 7000 had a bigger ion exchange capacity compared to the Nafion 117, which increases the concentration gradient on the surface across, like on both surfaces of the membrane, and the thickness of the CMI 7000 was bigger than the thickness of the Nafion 117. At lower, smaller, thinner membranes increase the concentration gradient, and they also are good for the diffusion of ions and the recovery of ammonium for our case. So we wanted, because these two membranes, they both have a good property and a bad property for the recovery of ammonium, we wanted to look at other parameters such as the diffusion coefficient and the separation factor that also affect the recovery of ammonium. And I'm going to present about the work on the separation factor. The separation factor is just a quantitative way of expressing the affinity of a membrane or the selectivity of a membrane for one ion. So like in our case, we are looking at the affinity of a membrane for ammonium over sodium. And this is the expression we use to evaluate that value. On the right picture here, I'm showing the setup for our experiment, in which the first flag in the back there is filled with ammonium and doesn't have any sodium. And we keep on decreasing the concentration of ammonium as we move up with the flask. And simultaneously, we increase the concentration of sodium to the point where when we reach the 6th flask, we do not have any ammonium and we only have sodium in the solution. This process was a little bit tedious, but with a lot of work, we were able to get some result. And yeah, I was excited to see that the result that we obtained. Here, I'm showing in the first, I would say first row of the slide. It is the separation factor for sodium, ammonium over sodium, and the bottom row are showing the separation factor for potassium over sodium. The green color is referring to the Nafion membrane, and the blue color is indicating the CMI 7000 membrane. What we observed here was that the Nafion 117 had higher affinity for ammonium and also for potassium over sodium, except for this one case where we looked at the total concentration was 100 milliequivalent per liter. And it may look like when we increase the concentration, the separation factor decreases, and that might be a negative point for our reactor setup. However, when we fill up the reactors, we usually have a higher concentration of salt in the raw solution and lower concentration in the waste solution, which with this difference in separation factor increases the concentration gradient and help with the diffusion of ammonium from the waste to the raw solution, which Michael is going to talk more about in the next slide.
All right, thank you, Oriel. Yeah, I didn't see any open question right now. So if you have any question, you can save to the end. And let's welcome Michael.
Thank you, Quay. Thank you, Oriel. And share my screen. Okay. As Oriel had mentioned, separation factors are essential for determining the membrane's affinity for ammonium and potassium over sodium in solution. The separation factors are also essential for the diffusion coefficients for ammonium and potassium as well. And so to determine the diffusion coefficients, we conducted non-analysis experiments with the CMI 7000 membrane, as well as the Nafion 117 for ammonium, as well as potassium recovery. And we were able to achieve much faster rate of recovery with the Nafion 117 membrane. The Nafion 117 membrane achieved 90% recovery of ammonium within 6 hours and 90% recovery of potassium within 4 hours, whereas the CMI 7000 membrane took 22 hours and 6 hours for ammonium and potassium respectively.
Hey, Michael, sorry. I think maybe you have the videos and something else that are up, and they're blocking some of the screen on the right and the bottom.
Let me close the, is that better?
Not yet.
I'm still seeing a box there.
Yeah, it's better.
It's smaller now, but there's another one at the bottom, kind of bottom right.
Right.
The only thing I can see is that the actual windows of you guys, and I just minimized it. So.
Oh, there's a small one which is hiding some of your experimental conditions as well. I don't know, is it coming from the Q&A box or no? Not sure.
Let me see something here.
Or maybe.
Is that better?
No.
No.
Let me stop sharing and then reshare.
Right.
Okay.
It's really
Strange. Yeah, it's Like all your other windows are minimized, right? Like the background.
I could try to.
If it doesn't work, we can also do like one of us can share the screen, and I mean that could be a possibility. But you can try the options first.
Yes, I think. Michael, do you want me to share the screen and then you can?
Sure. Apologize for the technical difficulties here. Am I sharing right now or not? Okay.
Give me 1 second. Okay. Which slide do you still remember? Like which one?
That was 23.
Okay. Yeah, Michael, you can start.
Okay. So to briefly recap, what I was saying was that the separation factors are essential for the diffusion coefficients, and that in order to determine the diffusion coefficients, we conducted non-analysis experiments with the CMI 7000 as well as the NaFi-17 membranes. And for the rate of recovery, we were able to determine that the NaFi-17 membrane was more efficient at ammonium and potassium recovery than the CMI 7000 membrane. And with the NaFi-17 membrane, we achieved 90% recovery of ammonium and potassium within 6 and 4 hours, whereas it took 22 hours and 6 hours with the CMI 7000 membranes. And also we used the Nernst-Planck equation in order to model our data, which is indicated by the red line. I wish I had my pointer, but we modeled the Nernst-Planck equation. We modeled our data against the Nernst-Planck equation, and we were able to determine the diffusion coefficients, which are on the next slide. Thank you. So again, with the modeling of the Nernst-Planck equation, we were able to determine diffusion coefficients for the NaFi-17 as well as the CMI 7000 membranes. And hopefully you can see in the image on the right that we had a much higher diffusion coefficient for the NaFi-17 membrane for ammonium than we did for the CMI 7000. In fact, it was on the order of 10 times greater. And but the diffusion coefficients were comparable or similar for potassium for both membranes. And although we're confident in our results, we were a little surprised to see that that both potassium and ammonium had dissimilar diffusion coefficients. It stands within reason that they would be dissimilar because they're different ions, but at the same time they have similarly charged densities. But the results are consistent with the non-analysis experiments that we conducted. Next slide, please. So now I'm going to switch gears briefly. Let's see, Quay and Kaylin, they talked about their work with urine. Litzov talked about his work with wastewater. And now I'm going to talk about Oriel and I's work with chicken poop. And with chicken poop, or more specifically, poultry litter, we were able to recover ammonium and potassium using a real waste stream. And one of the reasons why we chose chicken poop is because we live in the state of Maryland. And in Maryland, there's a huge number of poultry farms, particularly on the Eastern Shore, where it's in close proximity to the Chesapeake Bay, which is what Kaylin talked about earlier with the agricultural runoff. Historically speaking, many farmers have land applied that poultry litter to their crops in order to maximize crop yields. But again, that produces agricultural runoff, and that has created some problems, which is currently is a practice which is currently being restricted and regulated by the state of Maryland. So our lab was motivated to try to find a solution to this critical problem. And one of the things that we looked into was the possibility of extracting the nutrients from the poultry litter so that we could have a nutrient deficient poultry litter that could be applied as a soil conditioner, but also that we can have a source of nutrients for the precipitation of struvite, which, as Oriel pointed out earlier, has better crop yields as well as produces less agricultural runoff. Next slide, please. So to prepare a poultry litter extract, this is a method slide. I will just go through this briefly. To prepare our poultry litter extract, we took 20 grams of poultry litter and we added it to 1 liter of deionized water. And we acidified that poultry litter slurry to a pH of 4.5 in order to extract the nutrients. We then passed the poultry litter slurry through 25 micron filter paper by vacuum filtration. And then we syringe filtered the filtrate in order to produce a poultry litter extract that was devoid of particulate, which we were able to use in the IC to analyze the ion for determining an appropriate draw solution. Next slide. Here we have the chromatogram of the poultry litter extract. And hopefully you can see that the poultry litter has appreciable amounts of ammonium as well as potassium and magnesium, all of which are needed for the precipitation of struvite. One of the things we looked into was we wanted to provide a draw solution that would be strong enough to extract the nutrients from the poultry litter by dye analysis. So we took the total cation concentration of the poultry litter and multiplied it by a factor of 10 to come up with the concentration of 455 milliequivalents per liter of sodium chloride. And just for a frame of reference, this is has a lower salinity than seawater. And next slide. So again, we went back to the drawing board and we did dot analysis with the Nafion 117 membrane as well as the CMI 7000 membrane, but this time with real poultry litter waste. And we were able to recover 90% of the ammonium, potassium, and magnesium, as indicated by the top 3 figures on the left by dot analysis. And we were very pleased with this result because it took less than 10 hours to achieve 90% recovery. However, there were room for improvement. For example, as Oriel pointed out earlier, the Nafion 117 membrane has a lower ion exchange capacity than the CMI 7000 membrane, which disfavors ammonium recovery or potassium recovery for that matter. So we could optimize the system by replacing the Nafion 117 membrane with a membrane that has a thinner thickness as well as a higher exchange capacity. Also, we could optimize the system by incorporating a different draw solution. We incorporated sodium chloride as our draw solution, but we can consider other draw solution alternatives such as seawater, which has a higher salinity, or we can also consider reverse osmosis reject water, which is a traditional waste stream, which we could use for our beneficial purposes. And that pretty much concludes my portion of this presentation. And with that, I'd be happy to take any questions if there are any.
Thank you, Michael. I think there's one question opened. Oh, it's answered just yet. Yeah, I guess there are.
Just by looking at the slides, I don't understand much of how the experiments are being done, but apparently the Nafion membrane versus the CMI 7000 are really different. And if they are so different, why do you keep doing the Nafion? What is the purpose of continuing one of those tests that always give you such a lower number?
That's a good question. For the most part, the solutions that we work with were different every time. So we work with synthetic solutions and we got one result. We work with real waste. We got a different result in terms of like the rate of recovery. But most importantly, we did a sensitivity analysis. And it's not just the ion exchange capacity that you use to select the membrane. And it's not just the membrane thickness that you use to select the membrane. It's the combination of these factors that play a role in their rate of recovery. So although we didn't know later until after the sensitivity analysis that membrane thickness would play the greatest role, but prior to our sensitivity analysis, we just had two primary numbers, the membrane thickness as well as the exchange capacity. And this information alone is not sufficient to necessarily determine the best membrane for ion dialysis. However, it's a good indicator.
Okay. Thank you.
You're welcome.
So yeah, there are no more questions for you, Michael.
Okay. So
one thing I can add to one of the questions by the audience members, how cost effective are these membranes and how long do they last? So I think Oil, really hit some of the points about that this is not a pressure driven process, and we don't see like, unlike RO or nanofiltration where we have concentration, polarization, and a higher tendency for inorganic scaling. So here we don't have that. And then based on my practical experience of running these membranes. So when I was doing this work, we ran one of these membranes for like almost 300 hours using inorganic waste solutions, but also real waste solutions. So we did see, some decrease, I guess, but it was less than 10% over the course of these experiments. So there might be some amount of fouling of the membrane if you're using organic rich matrices, but I imagine it will not be as significant as we see for many other membrane processes. So I guess in that way, we can still employ these membranes, and maybe a future study can look into if we can like have some kind of a cleaning or wash methods where we can reduce that degradation of the membrane.
Yeah, thank you, Gustav.
Could I have, could you, someone could give a little bit of history on the subject matter? For example, is this something very new, or this is something that has been doing for several years or many years? Or this process of recovering nutrients, why is it, I don't know, a little bit of I don't know if it is something very new that is happening, and I only learned about this through Dr. Blaney, and I thank you so much. I want to, first of all, before that little history that you can give me, I want to say that some of the slides that were shown by Shazbat, example, slide number 12, explain really well the purpose for farmers, the process of the research and how it will benefit farmers. And you mentioned something very interesting about contaminants of emerging concern. That is something that we also have in ACS in our records. That is a presentation that Professor Blaney did, and is an excellent example of all the previous work that is being done, and that Dr. Shazbat refers to. Mm-hmm. So do we have, and you can find it in ACS webinars, and no, I'm sorry, not webinars, ACS recordings in our website. We also have, so can anyone explain a little bit the history of this research? why nutrient economy, why this circulatory need for recovering the nutrients, why this? How did it start? It is a long time ago, maybe 50 years ago, and now it's taking more, is becoming more important, or is just something very recent?
One things that Oriela mentioned earlier was the need to manage the nitrogen cycle. And that's something that that is a grand challenge of the national, identified by the National Academy of Engineering. And one of the reasons that this is considered to be a grand challenge is because it wasn't but so long ago that Haber-Bosch, I guess they developed the process by which they took atmospheric nitrogen and they reacted it with hydrogen gas in order to produce ammonium, which was needed to feed the world's growing population. And since then, the world population has just skyrocketed because of the availability of fertilizer. But this is a very energy intensive process. It takes 200 atmospheres as well as 400 to 450 degrees Celsius, in terms of temperatures under high pressure with the iron catalyst in order to produce, 10% yield of ammonium. So it's a very inefficient process, and it's also energy intensive. And in addition to that, we have wastewater treatment plants that take ammonium and convert it to nitrate, and then from nitrate to nitrogen gas, which is great for the environment, but it's a useless product because nitrogen does not readily react with anything unless it undergoes the Haber-Bosch again. So this is an inefficient cycle by which we have nitrogen in our environment. So the idea of a nutrient, circular nutrient economy is that if we could recapture ammonium after we use the Haber-Bosch process, if we can recapture that ammonium from agricultural sources or even wastewater, then we can decrease our dependence on the Haber-Bosch process, as well as lower our need for nitrification, denitrification processes, for the treatment of wastewater. So that's part of the nitrogen component for a circular economy.
Yeah, this is very interesting, and I thank you very much because we have nearby a water filtration plant and purification plant, and I was wondering if this type of recovering nutrients is being done in a larger scale already. Is it?
Yes, I can answer that one. And before that, I can also, like, when you talked about Don analysis, so I would just like to, direct it because Hue, as a first author, published a paper on recent advancements in Don analysis. So maybe Hue can give a little bit about like how Don analysis is something that, our lab has been able to, use for nutrient recovery. But in terms of large scale operation, yes, there have been some plants in the US and Europe. I mean, one of the plants which is the company is called Ostara, and they have a few operations in the US where they are recovering phosphorus, mainly phosphorus, but a little bit of nitrogen as well. And they are generating struvite, one of the products that some of us talked about. So the goal is, I mean, there are two goals. One is to limit the nutrients from getting into the bay or any other water bodies, and also then generating this value-added product that can be sold into the market. So there are some large-scale operations, and I think it's driven more by the regulatory framework rather than the need for recovering nutrients, but more from if there's a discharge limit. Or, many times struvite has been a nuisance for wastewater treatment plants. So how we can limit the amount of nutrients within the plant, and but at the same time recover it as a fertilizer product.
Yeah, thank you, Ustav. And I also can build some answer over yours. So in our lab, We do donor dialysis mainly for nutrient recovery. Like as I mentioned, we recovered ammonium, phosphorus, these kind of nutrients from different waste streams. But you guys can also check the recent review paper we just published. There are also a lot of applications for donor dialysis out there, and like metals recovery or etc. And there are also gaps over there. So I think that's all the opportunities for our future research. Yeah.
Great. And if I can just add to it, like donor dialysis, you know, because when I started looking at it, this is a process that conceptually it was, you know, I guess invented or conceptualized in the 1920s, but for different applications. I think only towards the 1990s, I guess, or 1980s, we see some use of donor dialysis for treatment of wastewater, where they were trying to remove certain contaminants like arsenic or uranium, which were at much lower concentrations. But from my knowledge, Dr. Blaney's lab really pioneered the work in nutrient recovery. So we are now dealing with a much concentrated waste stream where nitrogen and phosphorus are very high in concentrations. So yeah, so the process is old, but I guess the application has been, you know, evolving.
And maybe I'll just give some personal history too, if that's okay. I'm not one of the panelists. I'm a spectator here, but I think this is a great question. For me, and actually I'm so glad that Oriel and Kaylin were able to join here today as undergraduate researchers in the lab. I first learned about donor dialysis when I was an undergrad. It was actually my very first research project when I was an undergraduate student, using donor dialysis to recover iron and aluminum from drinking water treatment sludge, basically drinking water treatment residuals. And so we were doing some similar work, but there's some complexities to recovering nutrients, and there's a lot of opportunities for advances, you know, in the donor dialysis process, as all 5 of the panelists shared here today. But it was kind of cool for me because this was the very first thing I did, you know, as an undergrad researcher, you know, and now it's become a big part of our lab, as you can see, you know, these papers here on this slide, and you know, we have a big nutrient recovery team. During my master's, I was focused on phosphorus treatment in wastewater and kind of recovery. Recovery was part of the motivation, even though we didn't go too far down that route. But we were using kind of what we called hybrid ion exchange resins. So much more of an adsorbent than a membrane process, but that was kind of my first exposure to phosphorus and how important it is. And then I stopped thinking about nutrients for a long time. I went and I did my PhD. I moved up here to Baltimore, to Maryland. And then I got a phone call one day. And this guy, he said, hey, there's some new regulations coming into Maryland. This is the phosphorus management tool that Michael mentioned, you know, that are really going to affect farmers and make it hard for farmers, you know, to kind of do their business, protect the bay. You know, we need new solutions. And so that's when we kind of started like thinking again, okay, like I have experience with donor dialysis, I have experience with ion exchange, and I have experience with phosphorus. And so we put it all together and recruited, you know, this great group of undergraduate students, graduate students, and postdocs, you know, to come and really get some real solutions, you know, for our state. And so our work here, you know, it stemmed from that need, you know, that need for solutions in Maryland, while also kind of advancing the state of the science and, you know, kind of just general chemical, you know, knowledge and applied chemistry knowledge. And so, you know, it's been really cool for me because this is where I started, and now we're back there again. And so, yeah, thanks for that great question, Beatrice.
Oh, okay. Thank you for your support. You are the driving force of all this knowledge and all of this success of these students, or postdocs and doctors under your direction. It is becoming a very interesting set of recordings that we have with your presentations, that you already have 2 of them, and this one with your students is 3. And this is going to become like a very nice library for the students in the future. This is amazing. I really thank all of you for your participation, for your time, for your effort. You did an excellent job. I noticed that there were a lot of good comments from the people that that left, and I received in my cellular phone several phone calls of people saying that they were having a hard time getting in. I don't know how, but I believe they registered. They should have the link really easy to do it. But I received several. My phone was blinking, you know, like several people trying to get in, and I didn't know how to help them. Okay, so I really appreciate all your effort, all your work. It was a beautiful presentation, very clear, very well organized, very interesting. And I am so glad that it made connections with presentations that Professor Blaney did in the past, so that it will give us a connection. So I thank you very much, and let's hope that this will be another last Zoom meeting or webinar. Okay.
Thank you
Thank you so much for having us.
for having us.
Yeah, thank you so much.
Thank you for
All right.
having us.
You will be able to see yourselves also in one program that is called Webinar TV that they sent me recently. So I think this was taping there. If it is not, I will download it. And the recording will be available by tomorrow.
All right.
Okay.
Thank you.
Thank you.
Right. Thanks a lot. Okay.
All
Goodbye.
right, thank you.
Thank
All
Hi,
right, thanks for all
everyone.
the support from Maryland ACS. We love interacting with you all, so can't wait
Oh.
for the next opportunity.
Yeah, thank you so much. You have been so helpful, and so your collaboration is being fantastic. We really appreciate it. Yeah.
Thank you, thank you.
Right.
All right,
Thank
bye-bye.
you. All right, bye, everyone.
Bye.
Thanks to the other attendees as well.
Okay.